Hello everyone, welcome back to Clear Creek Solutions Hydrology Education videos. It's another Hydrology 101 video in the series, and today we're talking about snowmelt computations as it relates to hydrology and runoff and measuring the runoff from a certain site or location. You can download our free hydrology terms guide down below in the description box. It's a guide with over 100 hydrology terms that you can look up and use whether you're studying for something or you just want a quick reference. It's a great cheat sheet to get all the important hydrology terms that you need to know right in front of you. So if you go to the description box, you can get that for free. So let's talk about runoff from snow. Snow may remain on the ground for some time, but eventually it will melt and may contribute to runoff. In some spots of the western United States, melting snow produces the major portion of the annual runoff. Rates of runoff from snow are dependent on the heat available for melting. Computation of snowmelt runoff is a very different problem from the computation of runoff from rainfall. So let's talk about snowmelt physics. The heat required to melt snow comes from several sources. The most obvious source is solar radiation from the sun. Obviously, it's going to do a lot to melt the snow. The amount of radiation effective in melting snow is dependent on the reflectivity of the snow. Almost 90% of the radiation incident on clean, fresh snow is reflected without causing melt, while lesser amounts are reflected from dirty old snow. So if you have older snow that has dirt particles in it, it's going to reflect less and actually melt slower than the fresh snow that has just occurred. Because of the low heat conductivity of air, very little melt results from conduction in still air. So turbulence resulting from wind brings large quantities of warm air into contact with the snow where heat exchange can take place, if the vapor pressure of the air is higher than that of the ice surface. Since the heat condensation of water at 32 degrees Fahrenheit is 1073 BTU per pound, and the heat of fusion of ice is only 144 BTU per pound, the condensation of 1 unit moisture on the snow surface results in the melting of approximately 7.5 units of water from the snow. Since melt by convection of warm air and by condensation is dependent on turbulence, wind speed is an important factor in determining the melting rates. So rainfall also brings heat to the snow since the rain must be at a temperature above freezing. However, this doesn't impact the amount melted a whole lot. The amount of melt m sub s in inches of water caused by rainfall of p inches can be calculated by a simple calorimetric equation. M sub s equals p times t sub w minus 32 over 144, where t sub w is the wet bulb temperature in degrees Fahrenheit, and it's assumed to be equal to the temperature of the rain. If t sub w equals 50 degrees, 1 inch of rain will melt only about 0.12 inches of water from the snow, so close to about 12%. Rainfall is less important as a melting agent than is commonly believed. It is the warm air, strong winds, and high humidity that accompany rainfall that are responsible for cases of rapid melt during rainstorms. So people think, oh, look at all this warm water. It's raining on the snow that's causing it to melt. Well, not really. It's more about the overall weather change in the atmosphere that's occurring and less about the actual precipitation. With MWS and P in millimeters and T sub D in degrees Celsius, the equation becomes M sub S equals P times T sub W over 80. Equations and charts expressing snowmelt as a function of radiation, air temperature, vapor pressure, and wind have been prepared on the basis of theoretical concepts. Utilization of these relations in a practical computation of snow melting rates is difficult because of the wide variation in the important factors of a typical river basin and because the necessary data are usually lacking. Forest cover and topography influence wind and to some extent that temperature and humidity of the air. Methods of snowmelt computation are therefore approximations to the ideal conditions represented by the theoretical approach. So the common procedure for estimating rates of snowmelt in areas where the catchment is covered with a fairly uniform depth of snow is the use of degree-day factors. A degree day is defined for this purpose as a departure of 1 degree in a mean daily temperature above 32 degrees Fahrenheit. This is a day with a mean temperature of 40 degrees is said to have 8 melting day degrees. The degree day factor is the depth of water melted from the snow in inches per degree day, determined by dividing the volume of stream flow produced by melting snow within a given time period. So that's an encapsulation. That's a little overview of snowmelt computation. We're going to go more in depth in the next video. You can download that hydrology cheat sheets guide down below in the description, and we'll see you guys next time.